Welcome to West Grove Primary School's Math Workshop for Parents. I am Mrs. Nicole Chua, HOD of Mathematics. In this workshop, we hope to share with you math problem-solving strategies common to the upper primary, as well as support strategies to support your child in upper primary math. First, I'll give a brief recap on the math curriculum and syllabus, and the learning experiences your child will go through in West Grove Primary, before letting my colleagues Mrs. Ng Hui Ching and Madam Tay Yi Ting take over to share details of the various problem-solving strategies common to the upper primary and how to support your child in their learning journey. The math curriculum focuses on 5 aspects of learning, namely skills, concepts, processes, method connection, and finally attitudes. At the center of it all is the objective of nurturing all our students to be good in mathematical problem solving, which is also one of the key future skills. In West Grove Primary, we provide students with real-world contexts while learning mathematics using the Authenticity program. We also allow students opportunities to engage in games-oriented learning as motivated practice to master math facts with the GOLD program. On top of the syllabus, which spells out the skills and concepts that your child will learn throughout their 6 years of primary school, we also designed our own problem-solving strategies roadmap to arm our students with sufficient problem-solving strategies to solve most math problems. This goes hand in hand with the clue thinking routine our school adopts as a problem-solving approach to nurture process skills and method connection in our students. My colleagues, Mrs. Ng and Madam Tay, will go into more details about clue, the heuristics and problem-solving concepts of working backwards, remainder concept, and set theory. They will also share strategies on how you as parents can support your child at home. Thank you and enjoy your learning.
Hello parents, this is Mrs. Ng. I shall be sharing the following with you. Clue, a method our teachers use when teaching word problems. Number 2, a math heuristic known as working backwards. And towards the end of the whole presentation, I'll also be sharing 7 basic checks your child can carry out after doing the math questions. And lastly, some tips on how you can engage your child in math learning outside school.
This is the thinking routine our school uses to help guide our students to think actively when they do problem solving. The steps are as follows: comprehend, link, use, and examine. Clue in short. Comprehend is represented by C. It prompts our students to retell the problem by looking at the given information and looking at what the question is asking for. And L represents link. It prompts our students to make connections with similar questions or link information within the question itself so as to make a decision on what method or strategy to use to solve the problem. U means applying the strategy learned, and the correct use of formula and algorithm are very important here. And E stands for examine, checking for mistakes made in the use of the strategy. We'll talk a bit more about checking later. Okay, the first heuristics we'll be looking at is working backwards. Do you find the circles and the arrows familiar? As you can see from the content page of our problem-solving booklet, working backwards is a method our students have been exposed to since primary 2. When our students come across a question where they cannot seem to work from the beginning, they have to look for certain clues in the question, like starting values that are not given, but we know or can find the end result. Usually, the question asks us to find what the value is at first. Okay, let's take a look at the question on fractions. There were a total of 125 marbles in box A and box B. John took 49 of the marbles from box A and placed them in box B. In the end, there were 5 more marbles in box A than box B. So how many marbles were there in box A at first? So first, we look at what information is given. So there will be 125 marbles in total in both boxes. And therefore, 9 of the marbles in A were placed in B. And finally, A had 5 more than B at the end. Next, we also need to know what we do not know. We do not know the number of marbles in A or B at the beginning. So we cannot solve from the top part of the question, right? So we now know we have to use the strategy of working backwards. But before that, we need to see if we can make any connections between the information given or use any other concepts that your child had learned before. And we know that the total for A and B is 125. 9 of the marbles in A is placed in B. So there's internal transfer, all right? And then there's this fraction of a set. And there's also more than, less than concepts involved. So the concept and heuristics that we mentioned just now, actually our children were taught from P1 to P4. So what they learned in the previous levels, they really have to apply it on this question itself. Okay. Right, the question asks for the number of marbles in box A at first. So with all this information, how do we start solving? Okay, first we draw circles to represent A and B. Alright, and circles to represent the end results as well. So from the information underlined, we put them into the diagram. Okay, the arrows indicate the transfer of marbles. So we indicate minus 49 of A being transferred to B as minus 49 of A. Okay, so for B, it will be indicated as plus 49 of A because it's receiving marbles from A, right? So since the number of marbles in A was 5 more than numbers of marbles in B, but we do not know how many, we just put B as 1 unit and A as 1 unit plus 5. Okay, then we draw this comparison model to find the number of marbles in A and B at the end. And your child would have been taught how to draw this type of model in the middle primary, okay, the comparison model. Okay, so from the models, we equate 2 units, 1 unit plus 5 plus 1 unit. So 2 units plus 5 will be 125. And solving that, we find out that box B had 60 marbles and box A had 65 marbles. So now we can start working backwards to find the number of marbles in A at first. Since we are going to find out about the number of marbles in A at first, we make use of the information for A. So can we also start using from B? Yes, but I think for A is more straightforward, okay? So the question is, what fraction of box A is 65? Since there are 65 marbles in A at the end, right? So we ask the question, equate it to a fraction. So what fraction of box A is 65? So since 49 of A is being transferred to B, it means 59 of it remained, right? So putting the information into the part whole model, we know that 5 units is actually 65. Okay, and then we can find the 9 units, which is 117 marbles. That's the answer to the question. So your child is reminded to put A and S to indicate the final answer to this question. Okay, now we have to examine if our answer is correct. Okay, so how do we do that? We do that by finding out how many marbles are there in actually B at first, which was 8. Is 8. And then adding that to 117 in A, we have 125, which was actually the number given in the question itself. So I think we're on the right track in getting the answer. Okay, this is the second question. There's another type that will also require us to work backwards. Okay, so there were some passengers on board the bus, and at bus stop A, 2/5 of the passengers and 3 more alighted. At bus stop B, 1/3 of the remaining passengers and 2 more alighted. The bus had 10 passengers left. How many passengers were on the bus before reaching bus stop A? This is a lengthier question, but the method we use will be similar to the first question. Okay, comprehending the question means noting down what information is given. So in this case, 10 passengers were left at the end, 2/5 of the passengers and 3 more alighted from the first bus stop, and second bus stop, 1/3 of the remaining passengers and 2 more alighted. It's quite straightforward. What do we not know? Of course, we do not know the number of passengers on the bus at first, right? So we can't start solving from the top. So we're going to work backwards. So how does it look like? Okay, we can use two methods to solve this question. Okay, the first method uses the circles and the arrows, which is similar to the earlier question we have. So, but it also involves part-whole model, similar to just now. Okay, so as you can see, we start off with a bus stop A. When 2/5 of the passengers alighted, we indicate that with a -2/5 on the arrow. Similarly, we indicate 3 passengers alighting by -3. Okay, as you can see in the diagram. On the next arrow, okay, we carry on putting the rest of the information onto the diagram itself using the arrows and the boxes. So do take note that the fractions and the whole numbers are put on separate arrows. Okay, there's a reason for that. Later when you do the working, I think you should be able to figure out. Okay, now the only known value is the number of passengers left on the bus, which is 10. So we put that into the diagram as well. So now we are all set to actually work backwards. Okay, working back from the 10 passengers, we need to find out how many passengers there were before alighting at bus stop B, right? So we need to add 10 to 2. Because 2 alighted, we need to put the 2 back. And since 1/3 of the passengers alighted from B, it means 2/3 of the passengers remained. And hence, using only the numerator, we know that 2 units will be equal to 12. And we will find 3 units. Okay? And that will be 18. Next, to find the number of passengers before reaching bus stop A, similarly, we work backwards from 18 passengers and we add 3 back to become 21. So what fraction of A is 21? So since 2/5 of the passengers at bus stop A alighted, 3/5 must have remained. So 3 units will be equal to 21 and we find 5 units. Okay, which would be the total number of passengers at bus stop A at first. And that will come up to 35 passengers. So again, in the answer, your child is required to write A and S at the back to indicate that's the final answer for this question. To check for calculation mistakes or conceptual errors, we may work out the problem again from the beginning to the end using the answers we got from our workings, meaning we can use 35 passengers to start off and then we put that into the question and start solving. We should get 10 at the end. Okay, some students prefer this second method, which involves drawing of models and cutting it into units that you're very familiar with. Okay, so what do we do first? From the first underlined statement, we know 2/5 of the passengers alighted. So we actually cut the bar graph, not graph, sorry, bar model into 5 equal units. Okay, and we know 2/5 of the passengers alighted. So and then a plus 3 more. So we put this information all into the diagram as indicated here. Okay. So using the same reasoning, we cut the remaining model into 3 equal parts before indicating the number of passengers alighting at bus stop B. Okay, why 3 equal parts? Because 1/3 of the passengers alighted, so third we cut into thirds. That's why 3 equal parts. Okay. Finally, we are left with 10 passengers on the bus, and we put that into the last model that we have here. Okay, so please look at what is boxed up in red so that we can start working backwards. Okay, to find the passengers before they alighted from bus stop B, we need to be able to see that 2 plus 10 is actually equal to 2 green units. Okay, and we can find 3 of the green units to indicate the number of passengers that are before reaching bus stop B. So we know that 2 units is equal to 12, so 3 units will be equal to 18. Okay, this is the number of passengers who actually remain on the bus after leaving bus stop A and before coming to bus stop B. Okay, right. Now we look at the other box up part. So from there, we know that 3 units in blue is actually equal to 18 plus 3, which is 21. So to find the number of passengers before the bus reached bus stop A, we need to find 5 units, the blue colored ones, and it will amount to 35. Okay. And to check for accuracy of working, we can put our answer back into the question again and work from the beginning of the question. Okay, that's all for the next question. Thank you.
Hi, I'm Madam Ping Ying. I will now continue to share with you on the heuristic remainder concept, which can be actually presented in either the model diagram or by branching. Let's start off by looking at the next example. Question 3. Tim had 120 marbles. He lost 3/4 of them and gave half of the remainder to his brother. How many marbles had he left? Let's try to use the thinking routine clue to help us better understand the question. What are some of the information that we have on hand? First, we had the total number of marbles Tim had. We also know the fraction of the marbles remained after losing 3/4 of them, and we have the fraction of the remainder that is left. So what is some information that we do not have? We do not know what is the fraction of the total that is left. Let's link this question to our prior knowledge. Students have already learned how to draw diagrams and model diagrams. The following 3 skills are related to this question: part-whole model, fraction of a set, and multiplication of fractions. To solve this question, students can use the model diagram approach. First, divide the whole into 4 parts and identify one part to be the remainder. Now, since he is giving away 1/2 of the remainder, this suggests the part should be subdivided into 2 halves, as highlighted by the fraction half. Hence, the whole is divided into a total of 8 parts, as each quarter is further divided into 2. Since 8 units is equal to 120, the question asks how many marbles had it left, and that is equivalent to 1 unit, and hence 1 unit is equal to 120 divided by 8, which is equal to 15, which is the answer. Next, let's explore how to present our solution via the branching approach. By looking at the denominator 4, we first split the total units of 4 to 3 units and 1 unit respectively. Since the remainder of 1 unit is going to be further divided into 2, we hence look at the lowest common multiple of 1 and 2, which is 2, by reproportioning the initial 4 units to 8 parts, multiplying all by 2. We will then avoid having any fractions in our branching diagram. Hence, from this branching diagram, we can see that the total number of parts at first is 8. And hence, 8 parts is equal to 120. So the question asks for how many marbles is left, which is equivalent to 1 unit, and therefore the answer is 120 divided by 8, and hence the answer is 15. We should always encourage our students to check their answers. One way of checking is to check whether the answer is reasonable. Alternatively, when they have the excess time, they should always substitute back the answers they have calculated to see whether they fulfill the conditions given. For this question, we already calculated that a half of the remainder is 15. Hence, that means that the total remainder is 15 multiplied by 2, which is equal to 30. So 1/4 of the total is equivalent to 30, and that means that 4/4 of the total is equivalent to 30 multiplied by 4, which is 120, and that fulfills the condition of the question. Hence, the student will know that they have already calculated correctly for the question. Alright, now let's proceed to look at the next question. Yvonne spent $1,540 on a sofa. She spent 1/5 of her remaining money on a vest. She then had 1/4 of her original sum of money left. How much money did Yvonne have at first? Let's explore what are the information provided. First, we know the amount of money spent on the sofa. We also know that 4/5 of her remaining money is equivalent to 1/4 of her original sum. However, we do not have information on the following. We don't know the total amount of money. We do not know what fraction of the total is spent on the remaining amount. And lastly, we also don't know what fraction of the original sum is spent on the sofa. Similar to the previous question, students should link back to their prior knowledge on part-whole model, multiplication of fractions, and fraction of a set. To solve this question via model diagram, we first divide the whole to 5/5. But we do know that in 4/5 of the remainder, it is equal to 1/4 of the original sum. Using equal numerator and equivalent fraction concept, 1/4 is equivalent to 4/16. This means that the total number of parts in this whole should be 16 parts. Hence, the sofa will take up 16 minus 5, which is equivalent to 11 units, and hence 11 units is equal to 1,540, and hence 1 unit can be easily calculated. 1,540 divided by 11, and that gives us a quotient of 140. So to calculate the amount left, and that is equal to, to calculate the total amount she had at first, that will be equal to 16 units. So we use 140 multiplied by 16, and the product is 2,240, and that gives us the answer to be $2,240. If we solve via branching approach, using the denominator 5, we first branch out our total units to the sofa and the remainder. Having 5 units as the remainder, so that when we multiply 4/5 to the remainder, which is 5 units, that gives us a whole number of 4 units. Now, since 4 units is equivalent to 1/4 of the total at first, the total must be equal to 16 units, as 1/4 of 16 is equivalent to 4 units. Hence, the total number of units spent on the sofa is equal to 16 minus 5, which is 11 units. So with that, we can equate 11 units to be equal to 1,540. That allows us to calculate the value of 1 unit, and subsequently to find the total at first, we multiply by 16 and the product will be equal to 2,240. And that is the answer. Next, let's check and examine our answer. Apart from checking on the transferring of the data and if all information has been used, students can also use their calculated answer to check if it fulfills the conditions in the question. For example, in this case, given that the calculated answer is 2,240, this means that the remainder would have been the difference of 2,240 and 1,540, and that gives us the difference of 700. So 4/5 of 700 is calculated to be 560. If we use 1/4 of 2,240, that also gives us the same value of 560. So this fulfills the conditions in the question, and hence the student knows that they have calculated correctly. Now, let's explore the next heuristic, set theory and quantity times value. At first glance, some students may be mistaken the question to be of guess and check type instead. So let's find out the difference between guess and check and set theory or quantity times value. For guess and check, in general, the total quantity and the total value, in this case, the total number of sites, is given. The individual quantity of each type is not provided. For example, in this question, there are 60 triangles and squares. There are a total of 216 sites. How many triangles are there? For such question, the total quantity is provided and the total value of the sites. However, the individual quantity of each type is not. Students generally start with a random guess of the number of each type before arriving at the correct guess when the total quantity guessed matched the conditions given. Let's take a look at a question which deals with set theory and quantity times value heuristics. Question 5. There are 3 times as many triangles as squares. There are a total of 195 sites. How many triangles are there? For this type of question, there is usually a fixed ratio or proportion between the two types. In this case, for every 3 triangles, there is 1 square. We are also given the total number of sites. However, we do not know the total number of triangles and squares. For this type of heuristics, usually there will be a comparison where the proportion is fixed between 2 or more types of items. For example, there will be terms such as twice, 3 times as many, etc., or more or less than. The total value of the items are usually provided as well. If we solve via set theory, we can put 3 triangles and 1 square into one set, since the proportion is 3 triangles to 1 square. That means in one set, there are a total of 13 sides, since each triangle has 3 sides and each square has 4 sides. So that means one set, there will be a total of 13 sides. Since there are a total of 195 sites, we can calculate the total number of sets by dividing 195 by 13, and that gives us a quotient of 15. So there are a total of 15 sets. The question asks how many triangles are there in total. Since each set has 3 triangles, so 15 sets will give us 15 times 3, a total of 45 triangles, which gives us the answer. If we present via quantity times value, the idea is similar, but we present in the table form. Since there are 3 units of triangles, there will be 1 unit of square since the ratio is 3:1. Since each triangle has 3 sides, there will be a total of 3 units times 3. That gives us 9 units of sides from the triangle. Since each square has 4 sides, there will be a total of 1 unit times 4, which is equal to 4 units of sides from the squares. In total, that gives us the total number of sides to be 9 units plus 4 units, which is equals to 13 units. We are also told that there is a total of 195 sides. That means 13 units is equal to 195. With this information, we can then calculate 1 unit to be equal to 195 divided by 13, and that gives us a quotient of 15. The question asks for the number of triangles, and from the table you can see that the number of triangles is 3 units of value, so we can multiply the quantity 15 by 3, and that gives us the answer to be 45. Upon completion, students are encouraged to examine and check their answer. Some of the checking mechanisms include whether all information has been transferred and used, and whether there's any misread of data. Students should also use their calculated answer to work backwards to see if they fulfill the conditions of the question. For example, after getting the value of 45 triangles, that means that there will be 1/3 of the quantity of squares. So there will be 45 divided by 3, 15 squares. So calculating the total number of sides, they can calculate easily that the total number of sides is 45 multiplied by 3 to give you a product of 135 sides from the triangles. And then 15 multiplied by 4, 60 sides from the squares. And when you add up the two numbers, that gives you 195 sides, which is the conditions given by the question. So students will then know that they have calculated correctly. Let's explore another question. Sam sat for a quiz and the ratio of correct answers to wrong answers was 5:1. For each correct answer, 5 points were awarded, and for each wrong question, 1 point was deducted. Sam got a total of 96 points for the quiz. How many wrong answers did he give? For this question, the following information is given. The ratio of correct is to wrong is 5:1, and for every correct answer, 5 points will be added, and for every wrong answer, 1 point is deducted. The total number of points is also provided, and what is not given is the total number of questions in the quiz. In this question, using set theory, in every one set, there are 5 correct answers to every 1 wrongly answered question. So therefore, in one set, the points can be calculated. 5 multiplied by 5 equal to 25 points, but we have to minus away the one question that is answered wrongly, which we have to minus 1 point, which means that the total points in one set is equal to 24. The total points in this question is 96, so we can calculate the total number of sets by dividing 96 by 24, and that gives us a total of 4 sets. The question asks for how many wrong questions, so in every one set there is 1 wrong question, so 4 multiplied by 1, and therefore there is a total of 4 wrong questions, and therefore the answer is 4. If we present via quantity times value, the idea is similar, but we present it in the table form. If there are 5 correct answers, there will be 1 wrong answer since the proportion is 5:1. So in the table, we will record if there are 5 units of correct answers, there will be 1 unit of wrong answer. We also know that for each correct answer, there will be 5 points given. So under value, we will record it as 5. And for 1 wrong answer, we will have to minus 1 point. So using the quantity times value, there will be a total of 5 units times 5, which gives us 25 units of points from the correctly answered questions. And then for the wrongly answered question, 1 unit times 1, we will have to minus away 1 unit of points. So 25 unit minus 1 unit, the total number of points accumulated for this quiz will be equal to 24 units. We are also told that the total points accumulated is 96. So therefore, 24 unit is equal to 96. We can easily calculate the quantity of 1 unit by dividing 96 by 24. That gives us 4. The question asks how many wrongly answered questions there are. So from the table, you can see that that is 1U. So therefore, the answer is 4. Let's examine and check our answers. Apart from checking whether we have used up all the information given and whether there's any transfer error, we should also encourage our students to examine by working backwards using the information and value that they have already computed. Having 4 wrong answers means having 20 correct answers, as the proportion is 5:1. So that means there will be a total of 100 points accumulated from the 20 correct answers. 20 times 5 give you a product of 100. Minus away the 4 wrongly answered questions, which is minus 4 points. Therefore, 100 minus 4 gives you a difference of 96, and that fulfills the condition of the question. So the students will then know that they have calculated correctly.
The next segment will be to check for calculation mistakes. We always ask our children to check their work after they've finished doing. But do our children know how to check? Many a times they will just flip through the pages and say, yes, all are done. So here are 7 checks to minimize carelessness. Okay, the first one is misread, meaning your child might have written 243 as 234, making the working incorrect. Number 2, transfer of numbers or answers from the working space to the answer blanks. That's why we encourage your child to actually write down the ANS at the back of the final answer in the working space. So if he or she forgets to transfer the answer into the answer blank, the answer mark will still be awarded. Number 3, calculation mistakes, which is evident in adding, subtracting, multiplying and dividing, okay, the 4 operations. So you can teach your child to estimate the answers. For example, if the question is 29 times 5, then the answer will probably be close to 150 because 30 times 5 is 150. Number 4, reasonableness of answers. For example, the question asks for the number of children. Then your child gives an answer as 24 and a third. Something is not too right? And number 5, we must ask our children to make use of all the information given in the question. May it be a ratio, the percentage, or the fraction, or the whole numbers. Nothing should be left unused. And number 6, unit of measurement, which your child has to write in final answer when they answer questions involving length, area, and volume. And they have to remember to put brackets to the algebraic expression if the question asks for, something that involves a unit of measurement as well. And number 7, which is very important because is the question answered by your child? What do I mean? For example, if the question asks for the number of boys and your child calculates the number of girls, okay, then it is not that your child doesn't understand the question, but the child may have misread the question and interpreted it wrongly. So it's always good to check back to see whether they answered the question or not. So from today onwards, if your child says that he or she has finished checking the work, perhaps you can ask some of these questions to see whether they're all answered. Lastly, I should talk about parental support at home. As parents, I'm sure you will want to support your child in his or her learning of math at home. Other than helping your child to solve math questions, what else can you do to help your child in math? Well, let me show you some possible test questions and how they're related to your child's life. The first question is one that many parents encounter before the start of a new school term or year, which is to buy a bag for your child. You can explain to your child what discounts are and also how to calculate them so they can help them see how much money you can save through the discount. This question is on height, okay, about estimating the bookshelf, the height of the bookshelf in the school library. Okay, so when buying cupboards or furniture at, for example, IKEA or furniture shops, show your child the dimensions written on the price tag. You may also ask your child to estimate the length of your sofa or the bed at home. We also have questions asking your child to read scales. So do you have something similar at home? Perhaps a weighing scale or a measuring jug? What about this question? If your child does not know how heavy is one $1 coin, how can he or she still be able to estimate how heavy 8 of these $1 coins are? A method to let your child know how heavy a typical birthday cake is. It could be 500 grams, 600 grams, or a kg. Let the child try carrying the birthday cake. When you buy rice, perhaps let your child pick up a 2 kg pack, okay, so that they have a feel of how heavy an object is. All these would help your child make accurate guesses about how heavy these 8 $1 coins are. Would it be number 3 or number 4 as an answer? Would that be reasonable? Here are other examples of when we read scales in our daily lives. When we step on the weighing scale or when we watch a fruit seller weigh the bunch of bananas, which may be charged by mass. Or when we bake, we need to follow the recipe and use the right amount of ingredients where the measuring jugs come in. We see these two types of drinks often. Okay, so how can we use them to teach our children math? Look at the packet drink. We can ask our child to look at how what's the volume of a typical pack of this iced lemon tea, and on the pack itself, the volume is actually given. How about this cup of bubble tea? Why is it an A grade on this Nutri-Grade scale? Okay, so do you know to get an A grade, what should be the percentage of sugar in the drink? And how do you know? And the answers are all found on this page. Now we shall take a look at a typical receipt to see how we can calculate the total amount paid for a meal at a restaurant, inclusive of service charge of 10% and GST of 9%. In the case shown here, the customer paid $155.75. Why did he pay this amount when the total amount of food ordered was only $129.90? And how was this $12.90 and $12.86 calculated? Let's have a look at the calculations. Even though the subtotal is only $129.90, we have to pay a service charge based on the subtotal, which is $12.99, as well as the service charge. Okay, so the final amount paid will be the sum of the subtotal, service charge, and the GST. So here is one way to challenge your child further. You can show the final amount paid at the same restaurant. Let your child calculate the subtotal by working backwards. So we know GST is 9%. So we equate $155.75 cents with 109%. And we have to find 100%, which is the amount paid before GST and after service charge. It comes up to $142.89. So is this a subtotal? No, because it includes the service charge. So to get the amount before the service charge, we equate 110% with $142.89 since it's the sum of 100% of the subtotal and 10% service charge. Then we find 100% the subtotal. There are also other ways to engage a child in math learning. You can let them do budgeting when going overseas or doing grocery shopping, or converting units of measurement when they buy, say, milk, which is in liters. You can do a simple conversion into grams, or ml, milliliters, or let him or her weigh the vegetables that you buy at supermarkets. And perhaps also, if you're interested, let them plan the furniture in the bedroom if you're shifting to a new house. The list is not exhaustive. All you need is some creativity and imagination, and of course, having fun learning with your children in math. So we hope we have given you some ideas on some of the concepts and heuristics your child is studying in school, and how you can help your child apply math learning outside school. Thank you for your time, parents.